Your hypothesis was that iron should burn, so I have some steel tweezers.
Steel's mostly iron.
Steel is mostly iron, so let's try to burn the steel tweezers.
Okay, I think you're going to need something bigger than a big lighter.
Yeah, so we're going to up our power a little bit. Use a propane torch.
Yeah.
So let's try burning these tweezers.
No.
No.
Okay, wait, I got it. Remember what I said about solids and liquids have a hard time reacting? Why?
Less to interact with the air.
Let's interact with the air. There's not much surface area. Only the atoms and molecules on the outside can react. So of all the zillions of iron atoms, they're only the ones on the outside can react. So I think we should take those tweezers and put them in a blender and chop them up really fine. And then we got more surface area, and then we'll burn it.
Do you have a blender you're going to donate?
No, I was going to use yours.
Well, I'm not letting that happen.
Okay.
Let's try a different way to increase the surface area of steel.
What you got in mind?
I have steel wool.
Steel wool. Well, where did you find steel sheet?
Around.
Okay.
So, steel wool is fine fibers of steel, and I have like a little ball of it here. So let's try burning this.
Okay.
If I can get a propane to work. So it smokes and smolders a little bit.
It's not very impressive.
Not at all. Something on this one.
Okay, let's see. I think we've done about all we can with fuel. Okay, what about on the oxygen end? Anybody remember, I said air is about what percent oxygen? About 20%, so it's about 1/5 oxygen, which means of all the collisions with the molecules in the air, only 1 in 5 is with oxygen. The rest is mostly with nitrogen, which doesn't react at this temperature. It's really boring. So, what if every collision was with oxygen? What if we had 100% oxygen? I bet you've got oxygen.
I bet I have oxygen
I
here.
bet you've also got some sand in the bottom.
I do have some sand in the bottom.
What's the sand for?
The sand is to catch the hopefully molten iron.
Molten iron?
Yes. So let's see if we can get this to work, shall we?
This is pure oxygen.
That wasn't fast enough.
I think iron burns actually quite well in pure oxygen, doesn't it?
I think it does too.
Yay!
Yay.
So I was right. My hypothesis was correct.
Yes.
Iron does burn. We had to get it in some pretty extreme conditions, but we got it to burn. And actually, you saw that sparkle. When iron oxide forms, which is what we form when we burn iron, rust basically, it tends to flake off and make those sparks, which makes iron really sparkly, which is why they put it in sparklers, which are the fireworks used on 4th of July. By the way, the flame tests we're doing, they put those salts in fireworks too, so you can see the colors. That's the colors you see. It's always weird to go to a fireworks show with a bunch of chemists because they'll sit there and go, I think that's strontium.
You mean it's super fun to go to a fireworks show with a bunch of chemists?
Yeah, that's what I meant. Okay, so, now, it does occur to me that iron, Fe, from Latin ferrum, is right here in the middle, and I happen to know that these are kind of not very active metals. That's the ones that are really active, the ones that really hold their electrons loosely, the outer electrons, are over here on the left. Like this column. Like K. What does K stand for? Potassium. Oh, wow. Did you guys take chemistry or something? All right. That's great. You got K's potassium. All right. What's the Greek word it comes from? Calcium. Calcium for beautiful.
So
because it makes beautiful salts.
we have potassium in this jar right here. You can see the chunks in the bottom. We have to keep it in mineral oil. That's what the liquid is, because it likes to react with the air around it. So if we just left a chunk of it sitting on the shelf in our lab, it would react away and we wouldn't have anything to play with. So that's why we keep it in mineral oil. So I'm going to open up the jar and pull out a piece of the potassium. And it turns out potassium is actually a really soft metal, so we can cut it with a spatula. So we're pretty much cutting metal with a butter knife, which is a fun thing to tell your parents you can do, because they often don't know what I do, so, give them something. There we go. Now, this time we're going to react with oxygen, but we're going to have oxygen that's already part of something, right? So we're going to start with water. So water is hydrogen and oxygen. Okay. And we're going to dry off our potassium a little bit, get some of that mineral oil off. Okay. Okay. So I'm gonna hit the lights really quick.
I got it.
Oh, you got the lights.
I got the lights.
Everybody see? So we're just going to drop the chunk of
You guys in the
potassium.
front row, is your insurance paid up?
So we're just going to drop the potassium into the water.
Okay, so that was the reaction of potassium and water. Potassium and water were our reactants. Now let's use a little bit of theoretical background to see if we can actually figure out what happened. Now there's this guy named John Dalton who kind of figured out a lot of what happens in chemistry. He came up with a theory called the atomic theory back at the beginning of the 1800s. Now, by that time, a lot of elements have been discovered, and they were able to do that without even knowing about atoms and molecules. They knew about stuff, and they knew that if you broke some stuff down, you would eventually end up with stuff if it didn't break down into other stuff. And they called those the elements. And they knew a lot of them by then. They knew carbon and oxygen and phosphorus and calcium. Well, maybe calcium. They knew a lot of them. And they were measuring these things and trying to figure it out. And John Dalton came up with this idea. He said, what if every element was made up of little tiny bits called atoms, Greek for can't be cut, tiny bits, invisible bits, that were different for each element. And when they combined to form compounds, they just combined in different ways. That would mean that if you have a chemical reaction, you end up with the same number and types of atoms at the end that you had at the beginning. They're just rearranged. So let's try this on for size. Now, what did we have to start with in our reaction? What were our reactants? Potassium and water, right? Potassium's an element. Only got potassium added to it. What two types of atoms does water have in it? Hydrogen is not hydrogen and oxygen. Actually, you guys know this stuff. You've taken chemistry. Well, we'll do it again. Oh, you haven't? All right, good. Well, we'll do this for him. So, whatever we have in there now, we didn't make any new atoms. We have these three types of atoms to mess with. So, there's...
I'm keeping track.
You're keeping track, okay. We don't have any potassium left in there, except for a little bit melted and splashed up on there, and see.
Yeah.
Water splashed up.
Yeah, it did.
That's cool. But we do have this white stuff. And also, I remember seeing as that thing was going on, it was giving off a flammable gas that caught on fire, right? I guess that's kind of redundant. Flammable that caught on fire. And I know there are hydrogen atoms in there. Remember the balloon? Hydrogen, flammable gas. I'm guessing that hydrogen was
Liberated
and immediately caught fire and went right back to water. It enjoyed a brief existence as free hydrogen. It was like, I'm free, not anymore. But that leaves us with this white stuff, because there's no potassium, and it's got to contain the potassium in there. But it's not elemental potassium. The properties are different. It looks different.
Yes. It's like a white solid.
Yeah, because smoke is actually a solid suspended in the air. So I think that's potassium oxide.
Okay.
Yep, that's my hypothesis.
Your hypothesis is that we have potassium oxide just hanging out suspended here. So how are we going to test your hypothesis?
You just take my word for it.
Nope. Don't trust you that much.
Okay. Such a scientist. Okay, so I do know potassium oxide reacts with water. Most metal oxides react with water to make bases, and bases are the opposites of acids. So I think it's reacting right now with that water to make potassium hydroxide, which is a strong base. I think that water is basic.
So that, okay. So let's test this.
Yeah.
I have an indicator, which will tell us if it's basic, because it doesn't look any different
I
than
mean, it
water.
looks like water.
So indicators are a chemical compound that changes colors depending on if it's in an acid or a base. And so this one is the universal indicator. So it goes through the entire rainbow of colors, Roy G. Biv, where the red end is the acids and the violet or purple end is the bases. So if we add in some of our indicator, it starts off green, you can trust me, and we'll drop it in, see what happens. So it's purple, right? You see that? Maybe?
Very purple.
Very purple. So that would suggest that your
Very-
hypothesis is at least supported, if not true.
I'm going for 2.
Let's go with true. Okay.
Well, actually, we never can prove our hypothesis. We can just make it more likely. I think that hypothesis is a very likely hypothesis.
Yes. All right. So now we should probably neutralize this before we move on.
Yeah, because it is a strong base.
It is a strong base, so it's probably not safe to just have it sitting
Well,
there.
let's see. Base is what? How do you neutralize a base? Got an acid? Yeah. Did you bring that hydrochloric acid? No, not you. You right there.
Charge, right?
You didn't bring the hydrochloric. You got to stand with your lab. Did you bring the hydrochloric acid?
I left it in my glove.
You didn't bring any hydrochloric acid. We don't have the acid.
Well, okay, so we were just talking about how a metal oxide reacts with water to form base.
Yeah, it's called a base anhydride. Yeah.
Base anhydride. Okay. What if we use a non-metal?
Oh, we all got non-metal oxide because they react with water to make acid. They're acid anhydrides, and I breathe out a non-metal oxide. I breathe out carbon dioxide. We can do this.
That's going to take a while.
Good.
You want some help?
That would be a good thing. Yeah. It's
So
embarrassing.
instead of trying to breathe out enough carbon dioxide to form carbonic acid, we can just add some dry ice, which is solid carbon dioxide. We call it dry ice because it goes right from the solid phase to the gas phase. It doesn't melt in the middle, so that process is called sublimation. So we can add a chunk of that. The bubbles are the carbon dioxide gas, so they're reacting with the water. Should be forming carbonic acid, so it should be neutralizing, so it should be changing colors.
Yeah, it should be. I don't see anything.
Why don't we add another chunk? Go big or go home.
Okay, so I still don't see anything.
Just be patient.
You sure this works?
I'm pop. Yeah.
So what are we looking for?
Well, we're looking for a change in colors. Has it changed colors yet? What color is it now? What about now?
Green.
What about
Green's
now?
neutral.
So now it's greenish
Teal.
teal.
Teal's a duck.
Right?
So now it's about greenish yellow. Now it's yellow. So now we've gone slightly acidic. It won't go much farther than this because carbonic acid is not a strong acid.
And that's a good thing.
That is a good thing because carbonic acid is in soda pop, so you wouldn't want to be drinking a strong acid because that would ruin your esophagus.
That's right. Soda pop's carbon dioxide and water making carbonic acid. That's what makes it taste tangy. You put some sugar and some other unhealthy stuff in it. You got carbonic acid.
Okay, well, I think that dry ice is pretty cold. How cold is it?
So dry ice is about negative 95 degrees Celsius.
That's pretty cold.
That is very cold.
Yeah. Oh, we're not ready for that
We're
yet.
not
You got
ready
some
for
dry
that.
ice.
I have some dry ice here that I'd like to talk about before we get on to the really cold thing.
But it is cold.
It is cold. So, like I said, dry ice sublime, so that's the verb form of sublimation. So this entire time, we've had some chunks of dry ice sitting in this tank right here. So it's been subliming away, so we should have filled up our tank with carbon dioxide. And carbon dioxide is more dense or heavier.
Well, wait now. You're saying that's full of carbon dioxide.
I'm saying that's full of carbon dioxide.
That's your hypothesis.
That is my hypothesis.
So how are you going to prove it?
So I'm going to prove it by showing that we can float a bubble of air on top of our tank full of carbon dioxide.
Oh, like the hydrogen balloon was trying to float in the air?
Exactly. Since air is less dense than carbon dioxide, it should float on top. So let's
I gotta see
try
that.
this. Oh, hit the side.
I did.
Oh, that went in too much water.
When they're too small, it doesn't work. We do this. We do this.
Your hypothesis is wrong.
There we go. It just takes some time and practice.
Okay, so it floated in it.
It floated, so that was it floating on top of the carbon dioxide.
Okay, yeah, you're good. So now the cue.
Yes, now.
So that dry ice looks pretty cold, doesn't it?
Yeah, it was really cool.
Maybe about negative 95 degrees Celsius. So that's pretty cold. But most things will change to most gases. Well, most things are solids, liquids, or gases. And you can, if it's a gas, you can cool it down with a liquid. Most stuff, carbon dioxide goes straight to solid, and that's what solid is. We said air is mostly nitrogen. How cold do you think you have to get nitrogen to get it to condense into a liquid? Lower.
58.
Negative 58? Lower. Lower.
210.
Close. Negative 200 is pretty close. Negative 195 degrees Celsius. How cold is that?
That is really cold.
Well, we're just going to describe this stuff. We're going to just describe this stuff for them and not show them, right?
Well, we could show
You
them.
want to show them?
We can show them.
Okay, so.
So in this doer, that's what they're called. Sorry. We have liquid nitrogen, so it's liquid air essentially, or at least mostly. So we can just
Here, do some right here. Watch your feet. Told you not to sit on the front row. Where'd he go? Okay, it turns out that since it boils, if you condense it at negative 195 degrees Celsius, it boils at 195 degrees Celsius. That means to this liquid nitrogen, that tabletop of that surface is like a hot skillet. Just like water on a hot skillet. Goes. Now, what happens to gases as they get cold? We have a source of cold, so to speak.
yes. So I filled up this balloon with air. So we can try cooling down our balloon just by pouring the liquid nitrogen over it. See what happens.
What's that fog do then? Air has water vapor in it, and when it gets cold, it condenses out into tiny, tiny droplets. So that's water vapor condensing into fog. And now it's alive. The gases contract. And when it's cold, and when they're warm.
So when we heat it back up, it's back to the original size. So when we cool down a gas, it contracts. When we heat it up, it expands. And so we can do this over and over again with our balloon if we wanted to, because it turns out balloons are great scientific equipment.
All right. All right, yeah, give it up for Lonnie, would you? How are we doing for time? What? About 2 minutes? Okay. Any quick questions? 5 minutes? Okay. Any quick questions? You no. Any quick questions that don't involve you handling hazardous materials? Yes.
I am a physical chemist, so I'm a graduate student. I'm a physical chemist, so I study the physics behind chemical processes, and I'm a graduate student, so I have already gone to college to get my bachelor's degree in chemistry and physics, I came back to grad school to get my PhD, and so I use really big lasers to study how DNA replication works, which is really fun because you get to tell people that you work with lasers all day long, and then I do this job where I get to blow stuff up, so I'm kind of the stereotypical mad scientist, which I find really entertaining.
And she jokes about it. It's a lot of hard study and work, but she gets a lab. She's got a lab of her own, and she's got this big optics table on it and big laser. She turns it on, lights shine everywhere. And she shines lasers on single molecules of DNA to see to monitor what's going on as they fold or unfold.
It's quite fun.
It's amazing.
I highly suggest it.
Yeah.